Download this code from codegive.com, link in the description below. Training machine learning models efficiently, leveraging transfer learning. Transfer learning is a powerful technique in machine learning that allows you to leverage knowledge gained from solving one problem to solve a different but related problem. It's particularly useful when you have limited data for your target task, as it allows you to initialize your model with pre-trained weights rather than starting from scratch. This can lead to faster training, better performance, and the ability to tackle problems that would otherwise be intractable due to data scarcity. This tutorial will guide you through understanding transfer learning, its various approaches, benefits, and practical implementation with code examples using Python and popular machine learning libraries like tensorflow, keras, and pytorch. 1. Understanding transfer learning, the core concept. Imagine you're learning to drive a car with a manual transmission after having driven an automatic car for years. You already understand the fundamental rules of the road, traffic signs, and general vehicle control. You don't need to learn everything from scratch. You're transferring the knowledge you gained from driving an automatic to help you learn the nuances of a manual transmission. Transfer learning in machine learning works similarly. Instead of training a model from randomly initialized weights for a new task, you start with a model that has already been trained on a related task. The pre-trained model has learned useful features and patterns from its original task, which can be adapted to the new task. 2. Types of transfer learning. There are several approaches to transfer learning, depending on the similarity between the source, pre-trained model, and target, new task, domains and the amount of data available for the target task. Inductive transfer learning. Both the source and target tasks are different, but the domains are the same. The source task provides inductive bias, prior knowledge, to improve the learning of the target task. Example, using a model trained on a large text corpus to improve the performance of a sentiment analysis model on a smaller dataset of movie reviews. Transductive transfer learning. The source and target tasks are the same, but the domains are different. This often involves transferring knowledge between different data distributions. Example, using a model trained on labeled images of cats and dogs to classify unlabeled images of cats and dogs from a different camera with varying lighting conditions. Since you don't have labels for the target domain, it's transductive. Unsupervised transfer learning. Both the source and target tasks are different, and the domains are different. The aim is to use knowledge gained from an unsupervised task in the source domain to improve an unsupervised task in the target domain. Example, training a clustering algorithm on a large dataset of user activity logs to improve the performance of a clustering algorithm on a smaller dataset of sensor data. For this tutorial, we will focus on inductive transfer learning, as it's the most common type and often the most practical for real-world applications. 3. Strategies for implementing transfer learning. Within inductive transfer learning, we have a few key strategies to consider. Feature extraction. Freeze the weights of the pre-trained model and use its output, typically from the last convolutional layer or a fully connected layer, as features for your new task. You then train a new classifier, example a linear classifier, a neural network, on top of these extracted features. This is a good approach when you have a very small dataset for your target task or when the source and target domains are significantly different. Fine-tuning. Unfreeze some or all of the layers of the pre-trained model and continue training on your target dataset. This allows the model to adapt the learned features to the specifics of your new task. Fine-tuning is more effective when you have a moderate to large dataset for your target task and when the source and target domains are relatively similar. You can use a smaller learning rate than you used in the initial training, to avoid destroying the pre-trained weights too quickly. Asterisk pre-training and fine-tuning asterisk. This is essentially the full life cycle. Train your model, pre-training, on a large dataset, source domain. Then, take the trained weights from the pre-trained model and use them as initial weights for the target model. Finally, fine-tune the model on the target data. 4. Benefits of transfer learning. Asterisk increased performance asterisk. By leveraging pre-trained weights, you can often achieve higher accuracy and better generalization compared to training a model from scratch, especially with limited data. Asterisk faster training asterisk. Transfer learning significantly reduces the training time required to achieve satisfactory results, as the model starts from a better initialization point. Asterisk reduced data requirements asterisk. Transfer learning enables you to tackle tasks with limited labeled data, as the pre-trained model has already learned useful representations from a larger dataset. Asterisk improved generalization asterisk. By using features learned from a larger dataset, transfer learning can help your model generalize better to unseen data in the target domain. 5. Practical implementation with code examples. We'll demonstrate transfer learning using TensorFlow/Keras and PyTorch, focusing on image classification. We will use the pre-trained ResNet 50 model, trained on ImageNet, and fine-tune it for a smaller dataset, example a custom dataset of flower images. 5.1 TensorFlow/Keras example, fine-tuning. Explanation asterisk. 1. Data preparation asterisk. We use image data generator to load and augment our image data. Make sure your data is organized into separate directories for each class, example train/class1/image1.jpg, train/class2/image2.jpg, validation/class1/image3.jpg. Replace placeholders with your actual data paths. Class_mode equals categorical is for multi-class classification. 2. Load pre-trained model asterisk. We load the ResNet 50 model with weights equals ImageNet to use the pre-trained weights learned on the ImageNet dataset. Include _top equals false removes the final classification layer, the ImageNet classifier, allowing us to add our own custom classifier. We also specify the input _shape to match the expected input size of our images. 3. Freeze layers, optional. Initially freezing the layers is recommended, especially with small data sets, to prevent the pre-trained weights from being drastically changed during the first training phase. You can later unfreeze layers for more fine-grained fine-tuning. This stage is very crucial, without it your model might not yield good result. 4. Add custom classifier asterisk. We add our own fully connected layers and an output layer with a softmax activation to match the number of classes in our target dataset. Dropout is used for regularization. 5. Compile the model asterisk. We compile the model with an optimizer. Atom is a good choice, a loss function, categorical cross entropy for multi-class classification, and evaluation metrics. A small learning rate is crucial when fine-tuning to avoid drastically altering the pre-trained weights. A learning rate of 0.0001 or even smaller is a good starting point. 6. Fine-tuning, training. We train the model on our target dataset using the fit method. We specify the training data generator, validation data generator, number of epochs, and steps per epoch. 7. Unfreeze more layers, optional. After the initial fine-tuning with frozen layers, you can unfreeze the last few convolutional blocks of the base model and continue training with a very small learning rate, example 1 × 10⁻⁵. This allows the model to fine-tune the lower level features to better suit the target domain. 8. Evaluation, optional. Evaluate the trained model on the validation dataset to assess its performance. 9. Save the model, optional. Save the trained model for later use. 5.2 PyTorch example, feature extraction. Explanation asterisk. 1 Data preparation asterisk. The custom dataset class is used to load image data from a directory structure. Make sure the directory structure is as follows: your _ folder /train /class1 image1.jpg, your _ folder /train /class2 image2.jpg, your _ folder /validation /class1 image3.jpg. Transforms are applied to resize, augment, normalize the images. We then create data loader objects to iterate over the dataset in batches. Crucially, we normalize the images using ImageNet's mean and standard deviation, as the ResNet50 model was trained on ImageNet. To load pre-trained model asterisk, we load the pre-trained ResNet50 model using torchvision.models.resnet50, pretRained equals true. pretRained equals true downloads the pre-trained weights. 3 Freeze layers asterisk. We freeze the parameters of the pre-trained ResNet50 model by setting requires _grad equals false. This prevents the pre-trained weights from being updated during training. We are only training the new classifier we'll add. For modify the classifier asterisk, we replace the original fully connected layer, model.fc, with a new nn.linear layer that has the correct number of output classes for our target task. We retrieve the number of input features of the last fully connected layer and then overwrite that layer. 5 Define loss function and optimizer asterisk. We define the cross-entropy loss function and the atom optimizer. Critically, we only pass the parameters of the new fully connected layer, model.fc.parameters, to the optimizer. This ensures that only the new classifier is trained, and the pre-trained ResNet50 weights remain frozen. 6 Training loop asterisk. The standard PyTorch training loop iterates over the training data in batches. We move the data and the model to the specified device, GPU if available, otherwise CPU. The gradients are zeroed, the forward pass is performed, the loss is calculated, the gradients are computed using backpropagation, and the optimizer updates the weights of the new classifier. A validation loop is added for monitoring the model performance. Key differences between TensorFlow/keras and PyTorch asterisk. Asterisk data loading asterisk. TensorFlow/keras uses image data generator, which is highly convenient for image data augmentation and loading from directory structures. PyTorch often relies on custom dataset classes and data loader for more flexibility and control over data loading and processing. Asterisk layer freezing asterisk. In TensorFlow/keras, you freeze layers by setting layer.trainable equals false. In PyTorch, you freeze parameters by setting param.requires _grad equals false. Asterisk optimizer asterisk. In both frameworks, you need to carefully specify which parameters should be updated by the optimizer. In TensorFlow/keras, this is usually straightforward. In PyTorch, you explicitly pass the model.fc.parameters, in the feature extraction case, to the optimizer. For fine-tuning in PyTorch, you would pass model.parameters, to the optimizer to train all the model's parameters. Asterisk model definition asterisk. TensorFlow/keras uses a more declarative approach, defining the model structure by connecting layers, while PyTorch uses a more imperative approach, defining the model structure using Python code. 6. When to choose feature extraction versus fine-tuning. Asterisk feature extraction asterisk. Asterisk small target dataset asterisk. When you have very limited labeled data for your new task. Asterisk significantly different domains asterisk. When the source and target domains are very different, and the pre-trained model's features may not be directly applicable to the new task. Asterisk faster training asterisk. Feature extraction is generally faster than fine-tuning, as you are only training a small classifier on top of the pre-trained features. Asterisk fine-tuning asterisk. Asterisk moderate to large target dataset asterisk when you have enough labeled data for your new task to allow the model to adapt the pre-trained features to the specifics of the new task. Asterisk relatively similar domains asterisk when the source and target domains are relatively similar, and the pre-trained model's features are likely to be useful for the new task. Asterisk potential for higher accuracy asterisk fine-tuning can often achieve higher accuracy than feature extraction, as the model is able to learn more task-specific features. 7. Hyperparameter tuning and experimentation. Asterisk learning rate asterisk the learning rate is a critical hyperparameter for fine-tuning. Start with a small learning rate, example 0.0001 or smaller, and experiment with different values to find the optimal learning rate for your task. Asterisk number of epochs asterisk the number of epochs determines how long the model will be trained. Start with a small number of epochs and gradually increase it until the validation loss stops decreasing. Asterisk batch size asterisk the batch size affects the speed and stability of training. Experiment with different batch sizes to find the optimal value for your task. Asterisk optimizer asterisk Atom is a popular and effective optimizer, but you can also experiment with other optimizers such as SGD or RMSprop. Asterisk layer freezing asterisk experiment with freezing different numbers of layers in the base model. Start by freezing all the layers and then gradually unfreeze more layers to see how it affects performance. Asterisk regularization asterisk use regularization techniques such as dropout or weight decay to prevent overfitting, especially when fine-tuning. 8. Common pre-trained models. Asterisk image classification asterisk. Asterisk ResNet, ResNet 50, ResNet 101, ResNet 152. Asterisk Inception, Inception v3. Asterisk VGG, VGG 16, VGG 19. Asterisk MobileNet, MobileNet v2, MobileNet v3. Asterisk EfficientNet, EfficientNet b0, EfficientNet b7. Asterisk Natural Language Processing asterisk. Asterisk BERT. Asterisk GPT. Asterisk Transformer. Asterisk Word2Vec. Asterisk Glove. 9. Conclusion. Transfer learning is a powerful and efficient technique for training machine learning models. By leveraging pre-trained weights, you can achieve better performance, faster training, and reduced data requirements. This tutorial has provided a comprehensive overview of transfer learning, including its various approaches, benefits, and practical implementation with code examples. Experiment with different strategies and hyperparameters to find the best approach for your specific task. Remember that the right choice of approach depends on the similarity of domains, the amount of data available for your target task, and the computational resources available. With careful planning and experimentation, transfer learning can significantly improve your machine learning workflow.